I am Phillip Jang, and this is a brief presentation on Scalable Lévy process priors for spectral kernel learning to be published in NIPS 2017. This is joint work with Andrew Loeb, Matthew Davidow, and Andrew Wilson. Gaussian processes are rich prior distributions over functions with properties strongly controlled by a covariance kernel. Thus, learning this kernel function is vital for the generalization performance of the GP. And in our paper, we facilitate kernel learning by modeling a prior distribution over covariance kernels with a Lévy process. While GPs are typically used as smoothing interpolators, Wilson and Adams in 2013 introduced the spectral mixture kernel, which allows for long-range extrapolations with GPs. We can characterize a stationary kernel by its Fourier dual, shown in the second equation, and the spectral mixture kernel models a scale location mixture of Gaussians over the spectral density, shown in the fourth equation. In Wilson and Adams, the spectral mixture kernel is fit by maximizing the marginal likelihood with respect to the mixture hyperparameters theta. However, this approach does not characterize uncertainty over the hyperparameters, and furthermore, the number of mixture components J must be specified by hand and is assumed fixed. To address both of these points, we propose a Lévy process prior over spectral densities. Lévy processes serve as a natural process prior over parameterized basis expansions such as Gaussian mixtures due to the one-to-one correspondence between the jump behavior of the prior and the parameters of the expansion. Looking at the two figures below, we have on the left a realized sample path of a Lévy process with 3 jumps in total, and this will yield 3 basis functions in total, shown on the right. The locations of the jumps, indicated by the omegas, determine the parameter values of the basis functions, and the magnitudes of the jumps, indicated by beta, determine the weight assigned to each basis function. Note here that the number of jumps in the Lévy process is random, so we can model a random number of basis functions instead of fixing the number in advance. As a prior on spectral densities, Lévy processes yield some very powerful benefits, with the first and most obvious being the automatic selection over the number of mixture components J, as the Lévy process models J as random. The second is that it introduces sparsity-inducing priors over the mixture components, illustrated by the contour plots below. On the left two figures, the Gaussian and Laplace priors on coefficients yield L2 and L1 regularization. On the right two figures, the Lévy priors actually have inward curving contours, having an even stronger regularization effect than L1, and this aids in the removal of mixture components that fit to noise. A third benefit to our approach is its robustness to poor initializations, as our MCMC algorithm allows us to escape from poor initializations. Finally, our approach yields a posterior distribution over kernel functions rather than just a point estimate, and this allows us to account for kernel uncertainty in our predictions. Code is available, and I hope to see you at NIPS.